In physics, we draw batteries like this. The positive terminal is where charges have a lot of energy, so that terminal is big. The negative terminal is where charges have no energy, so that terminal is drawn with a small line. So here is a battery, and I'm going to connect it to a resistor. What happens when the charges are connected, when the battery is connected? Well, the positive terminal is where positive charges have all been congregated, and so they flow around the circuit. But they may not be flowing at the same rate in every possible scenario. If you take a really huge battery and connect it to a very small resistor, you are going to get a lot more charge flowing out all at once through that wire. So we need a way to quantify how much charge flows per second. Here's a resistor. We can imagine cutting the resistor right here so that we could separate the two sides and watch what happens. Now, if you cut the resistor, charge stops flowing. But if we pretend for a second that charge were to continue, then you would see charges passing on by. The electric field urges them along through the resistor. If you were to sit there, choose this cross-section right here, and count how many charges or how many coulombs pass per second, the amount of charge passing per second, or the rate at which charge flows, that is called current, and we give it the letter capital I. The unit for current, we can see, is the coulomb per second. A coulomb per second is defined as an ampere, which we give the letter capital A. So you might say that the current is 3 amperes, or you could say it's 2 milliamperes, but sometimes we call it amps for short, 5 microamps. There are a lot of factors that affect the current. We can imagine you have a medium-sized battery or a huge battery. A huge battery means there are tons of charges crammed into that positive terminal together. And so they're going to be flowing out much more rapidly because they have so much Coulomb repulsion. So not only does the potential difference affect the current, but there's something else that affects the current. It's the resistor that you connect to. This resistor, we can imagine, is pretty easy for charge to pass through. After all, there's a lot of space to go spread out. It's not very long, and also there's not many molecules in the path. But this resistor is much harder to get through. Positive charges really have to squeeze in because it's so narrow. And it's also really long, so that makes it harder. Plus, the molecules of the resistor are really dense, and so there's all this bumping around. It doesn't really happen easily. It takes quite a while to get through. We call that feature the resistance. We define resistance as the potential difference across a device, so from right here to right here, how much energy is lost per coulomb, and we divide that value by the current through the device. So if you choose a cross-section, how many charges or what amount of coulombs flows by per second. Resistance has units of ohms, and we use the Greek letter omega for that unit. So the top resistor might be 2 ohms, let's say, and the bottom one could be something much higher, maybe 200 ohms. What is an ohm, though? Well, if we look at the unit and the equation, we have units of potential difference divided by units of current. Potential difference is measured in volts, the same letter as the potential difference itself, and current is measured in amperes. So an ohm is just a volt per ampere. This equation makes sense intuitively. Let's take a 3 ohm resistor. We could connect it to a small battery, maybe 2 volts of EMF, or a huge battery, 200 volts. In which case does more current flow? Well, if you solve for current, having a bigger potential difference creates a bigger current. So more current flows out of the big, giant battery. But there's more we can say. If you imagine taking a 3-volt battery and connecting it to a really high resistance resistor, maybe 200 ohms, but then you connect the same battery to a smaller resistor, maybe 2 ohms, in which case is more current going to flow? Well, again, if we isolate current, we see that having a small denominator produces a high current. The smaller resistor makes it easier for current to flow, so more flows out, and here, less will flow out. We've learned that current is defined as the rate at which charge flows through a wire or resistor or any cross-section. We've also learned that resistance is defined as the potential difference across a device divided by the current through the device. Lastly, we've learned the official way of drawing batteries.